Okay, good afternoon all. Uh, it's an honor to be here to share my research work with you. My name is Ganta. I am from Opole University of Technology, Poland. My research title is Degradation of multiaxial fatigue strengths of laser powder-based fused marine steel in simulated corrosive environment. So we will look into experimental and machine learning analysis. My participation in this program is funded by Ministry of Science under Regional Excellence Initiative Program. These are the topics that I will be looking in my presentation. So let's start from introduction. So as we know, additive manufacturing has transformed a metal manufacturing process by simplifying a method to fabricate custom design complex high-strength parts. Unlike the conventional manufacturing process or primary metal manufacturing process, additive manufacturing, in our case, selective laser melting, produces a material by selectively melting the powder particle layer by layer. Even though the material produced by this method employed in a wide range of application areas, parts produced by this method resulted in reduced mechanical properties and surface characteristics, thereby affecting the structural integrity of material in corrosive environment. So as you can see from this shape and the intensity, the surface defects magnify the effect of corrosion compared to the internal imperfection. When we employ our material, when we use our material in air without corrosive environment, the actual acting load on our material is the effective load, which is equal to the nominal stress, the applied load. However, when we use our material in corrosive environment, the actual acting load on our material is the effective stress that considers the effect of corrosion through the developed corrosion pit. So these are the application areas and which is mainly affected by the corrosion, from the marine to the aerospace, and from the equipment that we use daily to the manufacturing industry. So in this all application, the corrosion affects the material sustainability through breaking the protective passive film and thereby creating the areas to crack initiation. So these are the previous research works conducted on marine steel material. So based on, from this literature review, we extracted these research gaps, which are lack of study on pre-corroded samples, limited study on the multi-axial loading, because most of study consider only uniaxial load, and inconsistent testing condition in the protocols, because most of study conducted by the corrosive environment, which is developed by manually, I mean the custom designed corrosive environment. And there are gaps in understanding the corrosion mechanism, and also there are contradictory findings regarding the effect of surface treatment, which is conducted on the same material. And also there is lack of study on investigating the main factors, which are weight percentage of corrosion medium and exposure duration. So to address these research gaps, we proposed this solution. We consider multi-axial cyclic loading. We followed the international standards, and we also conducted some tests to understand the corrosion mechanism, and we considered two significant factors in the corrosion. So in this research work, I used high strength, ultra high strength marine steel material due to it is excellent mechanical property, and also its weldability, which is widely used in selective laser melting process. So these are the chemical composition and the mechanical properties directly extracted from the material provider. So for this one is the experimental procedure and the setup that I have followed while conducting the test. So following STM E2207 standard, I printed this material with the presented dimension here. Then the printed parts are subjected to sandblasting operation and the heat treatment, again following the recommended heat treatment parameter. Then in the second stage, we exposed material to the corrosive environment, we like 7 and 14 days, which are 4 different groups considering the weight percentage of corrosion medium also. Then again, we employed cleaning operation, which are cleaning with deionized water, sandblasting operation, and manually picking the corrosion products. Then the samples were ready for further testing. So this is the results. So from now on, we will see the results. This one is the micro hardness result. So we conducted micro hardness on 16 points over 4 lines, and we obtained identical micro hardness value, as you can see here. Yes, there is a small variation, but this kind of variation is common in mechanical testing. Mainly, this is due to the employed cleaning operation on corroded and non-corroded sample groups. And we also employed sandblasting operation 2 times on the corroded group of samples. In contrary, here you can see the weight of this one is the weight loss, and the weight of the material is reduced following the corrosion, and this reduction is magnified for the samples which are exported for a longer duration. This is mainly due to the oxidation and the reduction reaction that took place between the surface of the material and the corrosive environment. So at the end of corrosion testing, we had 2 corrosion products, which are ferrous chloride and iron hydroxide. So this ferrous chloride we can easily wash by we can easily clean by deionized water, but for the iron hydroxide, we should use the manual picking process or sandblasting. So we employed 2. So the combined cleaning operation contributed to the demonstrated weight loss. Here we have the fatigue strength result for tension compression, torsion, and the combined tension compression and the torsion load. Here the green one represents for the reference without corrosion, the blue one after 7-day corrosion, and the black one is after 14-day corrosion. So as you can clearly observe from the first one and for the second one, which are for tension compression and the torsion, the corroded sample group demonstrated reduced fatigue stress compared to uncorroded group of samples. But in combined load condition, the effect of corrosion on the high stress level and the low stress level is different. So in the low stress level, the effect of corrosion is significant compared to the high stress level. Again, to confirm this, I conducted a corrosion damage analysis by using the equation presented here. So as we can see, for uniaxial, for tension compression and the torsion, we have positive corrosion damage, but under combined load condition, for some stress level, we have negative and the positive corrosion damage result. To support this with the statistical analysis, I conducted an analysis of variance based on the Takushi design of experiments. And as you can see here, we have this value, p-value, which is, if it is less than 0.01, the effect of that factor with its level is significant. So here we have the first one, which is the stress, the applied load, followed by the interaction effect of duration and the applied load. And the third one is the duration. So the effect of weight percentage of corrosion medium is insignificant in our case. Here we have the X-ray analysis, because the main intention was to study the effect of corrosion on the fatigue strength. So there should be no internal imperfections that falsify or affect our expected results. So here, as you can see, we have defects, but the defect which is these defects are characterized by less in diameter, less in volume, in the high spherical. So we published one paper, and we stated in that paper, if the internal imperfection is low in volume and high spherical, this kind of defect do not significantly affect the fatigue strength. So the only effect that's going to affect the fatigue strength of our material is the imperfection developed by the corrosion process. Here we have again the tomography analysis. So the main thing is, during the same analysis, I found that it's difficult to find the crack initiation and the propagation regions for the sample tested under torsion in the combined load condition. Because when we test the material under this condition, the crack initiates and propagates toward the Z direction. So it's difficult to find the crack initiation. So I used the results from tomography analysis, and I extracted the crack. So based on the crack topography, here we are going to discuss only for this sample. Here we suspect 2 regions as crack initiation, region A and the B. Here, region C, we can see it's clear crack propagation region. So to further locate the specific region that crack initiated, here I conducted further analysis, and I found that the crack was initiated from the surface defects, which is developed by corrosion. And compared to other pits, this corrosion pit has a high depth, which is that's the main reason why the crack is initiated from this load, from this corrosion peak. Under the combined load condition, we were expecting the crack propagation mechanism, it should be complex for 14-die corrosion, but we found that the 7-die corrosion demonstrated complex crack propagation mechanism, but 14-die corrosion demonstrated a short crack with only one crack. So the reason behind this is mainly because of the high heat depths, the high developed crack depths of the 14-die corrosion for the samples which are exposed for 14-die samples, and also the reduced load carrying capacity of 14-die corrosion. That's the main reason why we have the short crack and the only one crack, because it does not have time to propagate. I will skip this for the sake of time, and I will focus on this one. So here we have the fractography analysis. So as we said before, we don't have internal imperfection in the internal side of our sample. So we are expecting the crack, it should initiate from the outer surface or the inner surface of our hollow specimen. So as you can see, in all of the samples, cracks were initiated from the outer and the inner part of the specimen, as you can see here. And in some sample groups, the cracks were initiated from the subsurface defects. But as you can see, in these samples, their surface was mainly affected by corrosion. Even though the cracks were initiated from subsurface defects, its surface is mainly affected by corrosion. As you can see here, micro cracks, here also micro cracks. So considering all this effect of corrosion on the applied load, we developed a machine learning model following the SVR method. So we have 110 samples, but for each load condition, we have only 12 samples, which is significantly low. So to create a link between the input features and the output features, we employed the stress concentration factor and the weight loss for each samples. Then here we have the first function that relates the input features with the output, and during the training, during the model training, we try to minimize the model complexity and the prediction error by using these factors, this function, and with this function, the model can easily tolerate the complexity and accuracy. And here we have the final predicted value with the kernel function. We developed a model by using 4 kernel functions, which are linear, quadratic, and RBF, and also sigmoid. So from this all, we found that RBF kernel function resulted in a good prediction. As you can see here, we have the coefficient of determination. So here we validate a model, and you can clearly understand from this the prediction is quite good, because all of the data points lied within 2 times scatter band. Using the developed model, we predicted our fatigue strengths for 6 groups of samples. The first one is cyclic tension compression, torsion, and the combined load condition. The green one represents, the blue one represents for 7-die, and the red one represents for 14-die. So as you can see, for all tested conditions, for all predicted condition, the prediction mostly lied within 2 times scatter band, which is quite a good prediction. So to sum up our work, in the presented work, we printed a material by using SLM equipment, and we employed a cleaning operation, mainly considering the developed tensile residual strength on our material, and also to improve the surface characteristics. Then we subjected this material to corrosive environment. Then we tested microhardness, weight loss due to corrosion, and fatigue strength. Then further, we used the characterization method by using the tomography analysis, and the same analysis finally, based on this data, we developed a machine learning model. So here, the main results are the combined effect of electrochemical oxidation of steel, detachment of non-protective corrosion products through the employed cleaning operation contributed to the demonstrated weight loss, compared to the weight percentage of corrosion media, the concentration of corrosion media, the exposure duration significantly affected the fatigue strength. The analysis of VARIS or ANOVA analysis revealed that the stress significantly contributed to the variation in the fatigue strength, followed by the applied stress, duration, and lastly, with their interaction effect. And identical porosity levels and microhardness value were of time for all glucose samples. Under combined load condition, the effect of corrosion was significant in the low stress level compared to high stress level. The developed predictive model accounts for the effect of corrosion on multiaxial fatigue strengths, resulting in accurate prediction. These are the references that I have used in my presentation, and thank you for your attention. If you have any question, please welcome.